Study guide for test 3, problem 1. Prove that Z28 direct product with Z55 is isomorphic to Z20 direct product with Z77. Here we use theorem 8.2, which says that Zm plus Zn is isomorphic to Zm times n if and only if the GCD of m and n is 1. In order to use this theorem, we split 28 as a product of two relatively prime numbers. This is actually the prime power factorization of 28. 2 squared times 7. So 4 and 7 are relatively prime, and we can apply the theorem. So Z28 is isomorphic to Z4 plus Z7. Similarly, 55 is 5 times 11, and Z55 is Z5 plus Z11. So I get this isomorphism. And similarly, we work with 20 and 77. Split them as a product of prime powers and use the theorem. Z20 is Z4 plus Z5, and Z77 is isomorphic to Z7 plus Z11. And if you switch the order of some factors, you get isomorphic groups. So we reorder those to get the same order as here. This shows that Z28 and Z plus Z55 and Z20 plus Z77 are isomorphic because they are isomorphic to the same external direct product. Problem 2. What is the largest order of an element in this external direct product? Z21 is cyclic, generated by 1. The order of 1 is 21, and the order of any other element of Z21 will be a divisor of 21. So the largest order of an element of Z21 is 21, the order of the generator. This shows that the largest order of an element in this group, external direct product, is the order of this triple, 1, 1, 1. And the order of a triple is the least common multiple of the order of the components. The first one has order 21, the second one has order 14, and the third one has order 4. So the LCM of these numbers, how you find the LCM? You write prime power factorization of each number and then go over the prime powers. 2, the prime power of 2, the largest prime power of 2 is 2 squared, so it goes in the LCM. 3 to the first is the largest power that appears, so it goes in the LCM, and 7 is the largest power that appears. The largest power of 7 is 7. So this product is the order 84. Problem 3. Show that the subgroup L is a normal subgroup of the dihedral group D4. we apply theorem 9.1. A subgroup is a normal subgroup if x to the negative 1L x is a subset of L for any x in D4. If x is in L, then this is obvious because L is a subgroup, this is given, and when you compute in a subgroup, you cannot go out of the subgroup. So, we have to consider the other elements. Since D4 is the union of these two cosets, right cosets, L and L times R90, you can check. If you multiply L, the elements of L with R90 from the right, you'll get other 4 elements from D4. So this is the other coset. You know D4 has 8 elements. L has 4 elements, and this coset has the other 4 elements. So it remains to consider the case when this x is from the second coset, L times R90. It means that x will be y times R90 for some y from L. And we are interested in this inclusion, so compute this, x to the negative 1L x, but x is y R90. Now show SOX property. First the inverse of R90 and then the inverse of y, L y R90. And here we use that y is in L, so this is contained in L. That's why the whole product will be contained in R90 to the negative 1L R90. And it remains to prove that this is a subset of L. To see that, we just compute the elements in this set. This means that each element of L must be multiplied from the left with this and from the right with R90. If you multiply R0 with those two, you get R0. If you multiply R180 with those two, you get R180. And if you multiply D with those two, you get D prime. You can check this by drawing drawing a square. Label the vertices, apply from right to left, first R90, then D, then the inverse of R90. You'll see that the result is the transformation D prime. And this product is equal to the transformation D. So this is exactly L. So they are equal. Not only this is a subset of L, but they are equal. And we are done. Problem 5. Find the order of the element 3 times the subgroup generated by 15 in the factor group U16 factored by the cyclic group generated by 15. First, what are the elements in the cyclic group generated by 15? Here we have all powers of 15. They must be computed mod 16, and only two numbers are different. So this subgroup contains two numbers, 1 and 15 only. And 3 times 15 is this coset. Multiply each of these numbers by 3. And here you have to reduce mod 16 again. The result is 13. So the coset consists of these two numbers, 3 and 13. We compute powers of the coset until some power is equal to the unity of the factor group, and the unity of the factor group is this group generated by 15. 3 times 15 is not equal to the subgroup, so 3 times 15 squared, according to the definition of multiplication of coset, you have this. So multiply each number from the subgroup by 9, reduce mod 16, you get this. And clearly this is different set from this, so it is not the subgroup. The third power, again, computed similarly. Here reduce mod 16, you get this subset different from the subgroup. But the fourth power is exactly the subgroup, which is the unity of the factor group, which means that the order of this coset in the factor group is 4, the first exponent here that produces the unit. Problem 6. Let C star be the multiplicative group of the non-zero complex numbers and H the set of all complex numbers with absolute value 1. This is actually the unit circle. Prove that the factor group C star factored by H is isomorphic to R plus, which is the group of positive real numbers under multiplication. We use the first isomorphism theorem, theorem 10.3. We consider this map from C star to R plus that is defined with phi of z equals the absolute value of z. Clearly, the absolute value of z is a positive real number because C star consists of non-zero complex numbers. We have to prove two things, that phi is a homomorphism and the kernel of phi is H. Then the theorem, the first isomorphism theorem, will provide the desired isomorphism. If y and z are two numbers from C star, we have phi of yz is equal to this. The absolute value of a product is product of absolute values, and we have phi of y, phi of z. This shows that phi is a group homomorphism. The kernel consists of all z from C star whose image is 1, and this is obviously the unit circle. So this completes the proof. We just invoke the theorem and it produces the desired isomorphism.